one of the ways we can determine the concentration is by titrimetry. That's an acid-base titration. This is a technique for determining the amount of a certain substance by carrying out a titration experiment called volumetric analysis. So, as we can see, this is the setup for a titration experiment. Titration is one of the interesting experiments any students we like to do. Maybe because we normally have we have colors, and people like colors. Now, in carrying out a titrimetry or a titration reaction, we have a conical flask. Usually our base is in the conical flask. But when you get to the advanced stage in chemistry, you realize that not all the time we put a base. But for the purpose of this lecture, we shall still say we put the base in the conical flask. Okay? And then we put our acid in the burette. This is what our burette looks like. The burette is the one that is having that yellow tinge in the background. Okay? So, and then the burette consists of a tap at the tip or at the mouth. So it is from that we release gradually into the base in the conical flask. Mind you, that volumetry has to do with the fact that we need to take measurement of the volume of the base we are using. And then when we are titrating, we also take the measurement of the volume of the acid that has also reacted with the base. The base in the conical flask, we use a pipette to get the exact volume of the base. So we have a 10 ml pipette and a 25 ml pipette. So depending on which one we want to use, you can use a 10 ml pipette or we use a 25 ml pipette or whichever is available for use in the lab. Okay. So, and then just like I said earlier, we open the tap and release gradually into the conical flask. The conical flask with the base also contains phenolphthalein. Phenolphthalein is the indicator, because one of the beauties of the titrimetry or titration analysis is that we determine when we need to stop the reaction by a change in color. Now, moving on. Yeah. So a titration experiment involves the titrant, that's the solution in the burette, and the titrant. Titrant with T, that is our solution in the burette. In this case, it is the acid. And then the titrant, that is the solution in the conical flask. In this case, it is our base. So, and then when we open the tap of the burette and we allow the acid drop into the conical flask with a gentle swell, we'll just gently swell the conical flask and begin to observe. We will get to a point where enough acid or the titrant has been added to completely react with the titrant or the base. That point is called the equivalence or stoichiometric point. Okay. This point, how do we know we have gotten there? It's often marked by a color change in the indicator. The point where the indicator actually changes is the end point. This is where I normally tell students. Like, for instance, if you are using phenolphthalein, and or if it is a case of another indicator, like maybe methyl orange or methyl red or whatever indicator, that equivalence point you will notice that as you are adding the acid into the base, for instance, and you are using phenolphthalein, that color will be fading off. It will get to a point that the color will seem like, oh, it's almost colorless. When you get to that stage, you don't rush your acid into your base. It might just be one drop, just a single drop of the acid neutralizes the base, and then you have that color faded away. But students are not so careful. They like, some of you will like color so much. In fact, when you're going from pink to colorless, it's even pardonable, because of course, once it's colorless, there's nothing to look forward to. For some people, if you are going from a colorless solution, or maybe like from methyl orange, the yellow to pink, and they will want to see that beautiful pink before they stop the reaction. The more beautiful your pink is, the more you have deviated from the equivalence point, and the more you have deviated from the answer, and the more you'll be tending towards zero, to getting zero. So I normally tell students, once you see that immediate color change, that is where you are supposed to stop. But if you are looking for a beautiful color, the more beautiful that color is, the more zero you are going to get. The more you are tilting towards away from the endpoints, and that is dangerous for us. Okay, that means you're going to have, and you begin to wonder, they gave me a low mark. You get a low mark once you are looking for a very beautiful color. So, moving on. Yeah. So the goal is to choose an indicator such that the endpoint where the indicator changes color occurs at the equivalence points. Okay. So for different acids, for the different strength of acid, we have different indicators. If you are using a strong acid, strong base, the indicator, we can use a phenolphthalein. If you are using a strong acid, weak base, or strong base, weak acid, the indicator will be different. We need to know which indicator will be suitable at the equivalence point, because depending on what we are titrating, we could have a salt that is acidic, we could have a salt that is basic. So we need to have a good background of that to be able to choose the correct indicator that we use for our titration. So we have this showing us the procedure, the titration of an acid with a base. The flask contains the acid. Now, this time around, the acid was put in the conical flask, and you have a few drops of phenolphthalein. And we know that phenolphthalein is colorless in acidic solution. Now, on titrating and getting to the endpoint, that is in B, notice the faint pink color of the solution. Now, if we now go ahead, can you see what happened in C? Can you see the difference in the color between B and C? In C, the solution is well beyond the endpoint. Okay? Just like I was trying to explain, that the more beautiful your color is, the farther away you are from the endpoint. B is slightly, just faintly pink. You know that, yes, I have gotten to the endpoint. Okay? And you stop. But students are fond of making zobo. You see them, they'll continue to add until the color has turned beautiful, and then they'll think they have finished or they have ended the reaction. Meanwhile, they have gone far from the endpoint, and they will also go far from the actual mark. Moving on. We now want to take an example of calculation involving acid base. 0.5 molar hydrochloric acid, HCl, was titrated against 25 cm³ of an unknown concentration of sodium hydroxide. Use the data below to calculate the main titer. We are going to calculate two things. The first one is main titer. Now, normally we construct a table when we are doing our acid-base titrimetry. I'm sure you must have drawn a lot of tables when you were doing your WAEC or GCE and stuff, when you are doing the chemistry practical. So from the table, these are the values that we obtain. We have the rough titer, we have the first, second, third, fourth trial or titer value. From this titer value, we will need to look carefully and see which are the concordant values that we are going to use to calculate the mean titer. What do we mean by the concordant value? Concordant values in titrimetry means that those two values do not differ by more than plus or minus 0.2. The difference between the two values that you are going to use to calculate your titer should not be more than 0.2 plus or minus 0.2. So when we look at this, if you look at the first titer value, for instance, and the fourth titer value, the first and the fourth, you can see that the first is 27.9 and the fourth is 27.6. If you look at the difference between 27.9 and 27.6, the difference is 0.3. We cannot use those two values together to calculate our mean titer. The second, third, and the fourth, we can use the 3 because when you look at the values between 27.6, 27.7, and 27.6, the difference between them is not more than 0.1 cm³. So we chose the second and the fourth trial, which are the same value. We can actually add the third one and divide the value by 3. But anyhow you do it, don't just make sure that the values you are going to use to calculate should not differ by more than 0.2 plus or minus 0.2. So in calculating this, we decide to use the two values that are the same, 27.6 and 27.6 divided by 2, which is still the same 27.6. We could actually go for second, third, and fourth. We'll still fall within the same range. Moving on. The second part of the question. Calculate the concentration of the sodium hydroxide. That is the second part of the question. What information do we need? The balanced chemical equation. Always. As a chemist, what is important to us is not stories, but show us what happens when A and B react. Show us in just a single line by the use of a chemical equation. Nobody will deny you the mark. If you ask to answer a question and you put a chemical equation to show that, yes, this is what happens, it shows that you know the chemistry. Because as a chemist, we are so much interested in chemical equation. It says it all, that this is what is happening. Here we have sodium hydroxide reacting with the HCl to form sodium chloride and water. And looking at the equation of reaction, it is 1 mole of sodium hydroxide reacting with 1 mole of HCl. That mean titer we got from the previous question, we are going to use it. We'll convert to dm³, 27.6 cm³. Converting to dm³ by dividing by 1000 will give us 0.0276 dm³. From that, we calculate the moles of HCl. How do we get the moles? Concentration or the molarity multiplied by the volume. Because molarity equals number of moles divided by volume. So number of moles will be the volume multiplied by molarity. So we already know the molarity from the question we are given is 0.5. The number of moles as the volume from the title value 0.0276. So when we multiply that together, we get 0.0138 moles. Next, when we look at the equation of reaction, we already said 1 mole of HCl will require 1 mole of sodium hydroxide. So it means the number of moles is equal. It's a 1-to-1 ratio. Meaning that the 0.0138 moles of the HCl that we have calculated, we also require 0.0138 moles of sodium hydroxide. And then we use that to calculate the concentration of sodium hydroxide by dividing the number of moles by the volume. The volume of sodium hydroxide given is 25 cm3. So when we convert 25 cm3 to dm3, we divide by 1000 to get 0.025. So dividing the number of moles, 0.0138 by 0.025, will give us our concentration of sodium hydroxide, which is 0.55 molar. I hope we are following. Let me check the chat. Do we have any question? Okay. Now, the next type of reaction we'll be looking at, I have some practice questions here. I will send this slide to you through your classroom. We have some practice questions here. In fact, I think the answer have been given so that when you calculate, you can verify if you got the answer correctly. I'll send the slides to your classroom, please. So we are moving on to the next type of reaction, which is redox, reduction oxidation reaction. Oxidation and reduction reaction. What is oxidation? There are different ways we can define oxidation. You see, oxidation and reduction, when you try to visualize it, it's like somebody wants to give out something, and somebody is willing to collect. If I want to give out something and nobody is willing to collect, then there is no use giving out. If I want to receive something and nobody is willing to give me, then no, I will just be there, nothing to receive. So usually oxidation and reduction, they go hand in hand. That's why we say redox, a redox reaction. Where you are seeing oxidation, there will also be an equivalent reduction taking place. So they go together. They are 5 and 6. Like they will say it in the slang, say 5 and 6. What are the different ways oxidation can take place? The first thing is addition of oxygen. We can define oxidation by saying we have added oxygen. Another way we know that oxidation has taken place is increase in oxidation number. If there is an increase from 0 to 1, or 1 to 2, or 2 to 3, we say oxidation has taken place. Increase in oxidation number. The third way by which we know that oxidation has taken place, or a way of oxidation, an oxidation reaction, is removal of hydrogen. And the last way is removal of electron, or we say loss of electron. So oxidation is accompanied by loss of electron. All what we have said about oxidation, the opposite will be for the reduction. Since we have said they go pari passu, wanting to give and wanting to collect. Okay, one is wanting to give electron, the other is willing to collect. Okay, so all what we have described in the oxidation, the opposite will take place for in the case of reduction. So in a reduction, we have removal of oxygen, decrease in oxidation number, addition of hydrogen, and addition of electron, or we say electron gain. In oxidation, it is electron loss or loss of electron. In reduction, it is addition of electron or electron gain. Now, we also describe them by what they do. In redox reaction, we have reducing agent and oxidizing agent. Reducing agent is the one that causes reduction, or reducing agent, it is the one that will reduce the other party. While it is reducing the other party, itself is oxidized. So they are, just take note, always, reducing agent is oxidized. Reducing agent is the one that reduces the other, but itself is oxidized. Oxidizing agent is the one that causes oxidation to take place while itself is reduced. I hope we are following. Moving on. Now, in terms of oxidation state or number, how do we know what is the oxidation state or what is the oxidation number? It is the charge the atom will have if the shared electrons were divided equally between identical atoms bonded to each other. We shall see with examples. How do we assign this oxidation state? The first rule, or the rules for assigning oxidation state, is that the oxidation number of a neutral atom or an element is 0. For example, sodium metal is an element. The oxidation number is 0. Still in its original state without it getting involved in any reaction, the elemental state. Sodium as a metal has oxidation state or oxidation number of 0. Oxygen gas, oxidation number will be 0. Phosphorus, oxidation number is 0. So all the elements in their neutral state, they all have 0 oxidation state or 0 oxidation number. Secondly, the sum of the oxidation numbers of all atoms in a neutral compound is 0. For instance, you have sodium chloride. Here, in this sodium chloride, it is no longer sodium metal like we saw in the example in number 1. The sodium here has +1 oxidation state because it has lost 1 electron. The chlorine or the chloride ion has gained an electron. So in the sodium chloride, you have +1 on sodium, -1 on chlorine, +1 -1, 0. The sum of the oxidation number of all the atoms in a neutral compound is 0. For an ion, the sum of the oxidation number is equal to the charge on the ion. For instance, the phosphate ion, PO33-, the oxidation number on this phosphate ion will just be the charge on the ion. The charge on this ion is -3. So the oxidation number of PO3 is -3. PO3 ion is -3. So just look at the charge on the ion. That equals to the oxidation number on the ion. Number 3, the oxidation state of a monoatomic ion is the same as its charge. One, monoatomic, that is one atom. So for instance, Na+, the charge on it is +1, the oxidation state is +1. Cl-, the charge on it is -1, its oxidation state is -1 as well. Ca2+, the charge on it is +2, therefore its oxidation state is also +2. The next rule is that oxygen in a compound usually has an oxidation number of -2. That is, anytime oxygen combines with another element, its oxidation number is usually -2, except in peroxides, where it has an oxidation number of -1. Hydrogen usually has an oxidation number of +1, but when it combines with a metal, its oxidation number changes -1 because the metals are always positive, especially the metals will have electropositive. They will have positive oxidation state, so hydrogen will be the one to carry the negative sign. All group 1 metals have oxidation number of +1. Group 1 metals, lithium, sodium, potassium, cesium, and rubidium, they all have oxidation number of +1. All group 2 metals have oxidation number of +2. Beryllium, magnesium, calcium, and so on and so forth. All the members in that group, they have oxidation number of +2. Now, just as a quick one, we are asked to determine the oxidation number of Al in Al2O3, phosphorus in H3PO4, sulfur in SO3 2-, nitrogen in NO3-, It's a very simple question. Now, they are very simple questions. Yes, I can see people providing answers already. Yes, put it in the chat box. Aluminium is +3. That is very correct. I'm reading the chat box. So anyone who has attempted, put your answers in the chat box. Yes, we have all agreed. Aluminium is +3. Let's go to the next element. Phosphorus. Phosphorus is what? +5. Yes, that is very correct. What is the next one? Sulfur. Put your answers in the chat box. Let me see. What is the oxidation state of sulfur? Oh, we are having different answers for sulfur. I can see +4. I can see +6. I can see +2. So what is the correct answer for sulfur? What is the oxidation state of sulfur? Sulfur is +4. Sulfur is 4. The oxidation state of sulfur is 4. How do we know it is 4? Sulfur, if you assume it is X, and then oxygen is -2. -2 multiplied by 3, that is -6. So X minus 6 equals to the total charge. X minus 6 equals to -2. So if you take -6 to the other side, X becomes -2 plus 6. That is +4. And then nitrogen, which is the last, the D question. N in nitrates. What is the oxidation state of nitrogen in the nitrate ion? Yeah, that is +5. Very correct. Well done, well done to everybody for attempting the question. Thank you. Now we have another question here. Determine the reducing and oxidizing agents in the reaction below. So we have CH4 plus oxygen to give CO2 plus water, all in the gaseous state. So if you remember, we said the reducing agent is the one that is oxidized. The oxidizing agent is the one that is reduced. And we have different ways that we have used to highlight or define oxidation and reduction. So if we look at this CH4, what happened to CH4? What happened to oxygen? Which one of them involves removal of oxygen or addition of oxygen or removal of hydrogen? You know, that is one simple way to use to detect which one has been oxidized and which one has been reduced. So type your answer in the chat box. Let me see. Which one is the reducing agent? Which one is the oxidizing agent? CH4, I can see so many CH4 is the reducing. Is that true? CH4 became CO2. That is removal of hydrogen or addition of oxygen. It is the one that is oxidized. Therefore, it is the reducing agent. That's very correct. While oxygen is the oxidizing agent. So that is very good to see that you are understanding and following the class. Yeah, CH4 to CO2, reducing agent. 2 oxygen to water, oxidizing agent. Very correct. Very correct. I'm very happy with this. If you were in class, I would have told you to clap for yourself, but you can still clap. You do a virtual clap. Now, moving on. Balancing of redox equation. Our redox reaction will occur either in an acidic medium or a basic medium. The first one we are going to be looking at is the acidic medium. How do we balance our reaction, our redox reaction, if it is occurring in an acidic medium? This is an example. We have MnO4 minus plus Fe2 plus to give us Mn2 plus and Fe3 plus. The first step is to identify the oxidizing and reducing agents and then write the half equation. Just like we just identified the oxidizing and reducing agents in the previous equation we just looked at, the same way we are going to identify using all the definitions that we know about oxidation and reduction. Which one is the oxidizing agent? Which one is the reducing agent? So can I see you type in the chat box before I show you the answer? Our oxidizing agent or reducing agent will be taken from the reactant. So I can see somebody putting a product. No. Out of the 2 reactants that we have, which one is the oxidizing agent? Which one is the reducing agent? Okay, I can see answers here. MnO4 minus is the oxidizing, Fe2 plus is the reducing. Very good. Now, let's see what we have here. How do we know? MnO4 minus gains electrons. So it acts as the oxidizing agent. Therefore, it is reduced because it has gained electron from MnO4 minus to Mn2 plus. So the half equation for that is MnO4 minus going to Mn2 plus. Also, when we look at it in terms of oxidation number, we have said reduction. If we are defining reduction in terms of oxidation number, is what? Decrease in oxidation number. If you look at the oxidation number of manganese in MnO4 minus, it is +7. If you look at the oxidation number in Mn2 plus, it is +2. +7 to +2, that is reduction in oxidation number, which amounts to a reduction reaction. Okay? Fe2 plus loses an electron. Therefore, it is the reducing agent and it is the oxidized one. It is the one that is reducing the other one, while itself is, it is one that is reducing MnO4 minus, while itself is oxidized. So the half equation for that will be Fe2 plus going to Fe3 plus. That is the oxidation half reaction. Now, step 2. For each of these half reaction that we have written, we balance all the elements except hydrogen and oxygen. The previous one we have written, MnO4 minus going to Mn2 plus. If you look at it, let's go back again. We have one manganese on the left-hand side, and we have one manganese on the right-hand side. So manganese is balanced. If we look at the oxidation half, we have 1 mole of Fe2 plus on the left-hand side, and we have 1 mole of Fe3 plus on the right-hand side. There is nothing to balance in terms of elements. So we have fulfilled that condition. Balance all the elements except hydrogen and oxygen. In our own case, all the elements are balanced. So we have fulfilled that condition. The next step, balance all oxygen using water. For each oxygen, add 1 mole of water. Now, if we look at MnO4, we have 4 oxygen there. So on the other side, we are going to balance it with water. So 4 oxygen on the left-hand side, we translate to adding 4 moles of water on the right-hand side. Balance all oxygen using water. Now, the next one says balance hydrogen using H+. Because we have introduced water, there is now hydrogen. How many hydrogen do we have? 8. For each of those hydrogen, you replace or we add H+. For each hydrogen that we need, we'll add H+ on the other side. We have already seen that we have 8 oxygen on the right-hand side. So on the left-hand side, we are going to add 8 moles of hydrogen ion. I hope we are following. The next thing is balance the charge using electrons. Now, for MnO4 minus, we have said the oxidation state is +7, while the Mn2 plus is +5. The difference between them, 7 and 5, 7 and 2 is 5. That is why we are adding electrons. Okay? Another way we can look at it is that we have 8 hydrogen ion. That means we have 8 plus. On the manganese ion, we have -1. 8 minus 1, 7. On the other side, we have +2. Okay? So, on the right-hand side, we have a total of -7. On the left-hand side, we have a total of +2. Sorry, on the left-hand side, we have a total of +7. 8 minus 1, 8H plus, -1, +7. And then on the right-hand side, we just have +2. So to balance it, we use electrons. So 8 minus 1, 7 on the left-hand side, and then 2 on the right-hand side. 7 minus 2, 5. That is why we are adding 5 electrons on the left-hand side. So when you calculate the number of charges, you have 8 plus and -1. That is +7 on the left-hand side. And then on the right-hand side, you have just +2. The difference between them, 7 and +2 is 5. So for each charge, you add 1 electron. So we have 5 charges, so we are adding 5 electrons. Now, the other half, the oxidation half, Fe2 plus going to Fe3 plus electron. We are now trying to put them together. The first half has 5 electrons. The second half equation has just 1 electron. So the step we are going to take, it says, if necessary, multiply one or both balanced half equation by an integer to equalize the number of electrons transferred in the two half reaction. That will lead us to multiplying the oxidation half by 5 in order for the electrons to be balanced. Because in the reduction half, we have 5 electrons. In the oxidation half, we will have just 1 electron. So when we multiply that by half, we'll now add them together. Okay? When we put them together, we see that 5 electrons from the reduction half equation and then 5 electrons from the oxidation half equation are common. We can cancel them out. And when we cancel them out, the final equation now becomes 5 moles of Fe2 plus 8 hydrogen ion plus MnO4 minus to give us Mn2 plus 12 moles of water plus 5,3 plus ion. And that is the balanced equation. So that is how we balance in acidic medium. Do we have any question? Because that is where you are going to stop today. We'll continue from there on Friday. If you have any question, I'm looking at the chat box now. Okay. In the absence of any question, we'll stop here today and continue from there on Friday. So before Friday, I will send the slide to the class rep so that whatever practice question I have put there, you do it. And then if you have any question, you bring it to the class. I'll also see if I can get more practice questions so that when we finish the class on Friday, if we have more time, we can take more practice questions in order for us to solve any problem that we are not clear with. We will be told if it is acidic. You are asking to know. Don't worry. When we are giving you the question, we'll specify balance the following in acidic medium or basic medium. So we'll tell you. You don't need to worry your head about that. So I'll see you at 9 a.m. on Friday morning for the concluding part of the class. Do enjoy the rest of the day. Thank you.